See, there's a different type. No. Oh, okay. So most of these look to be the same type. Here's a different kind of idea that's given in this section. I think I've talked about this before. Yeah, we've done this before. I'm almost certain, but let's formalize this. We talked about this kind of triangle before, right? 3, 4. Anybody remember what the other side was? 5. There's a 3, 4, 5 triangle because 3 squared plus 4 squared, 9 plus 16 equals 25, 5 squared. Right? So if I had similar triangle, similar triangles means the same triangle just blown up or shrunk. So it's going to be multiples involved. So if I had another triangle that was similar to this one that had, wow, this was 12, and I'm like, well, what's that side? That one's easy. Well, may not make you feel too bad if it's a little freaky, but this is an easy example of this kind of problem. Well, let me show you how to do it mathematically. This is really nice. You can set up all kinds of proportions between the two. So if these are similar triangles, that means that the proportion, that the ratio 3 to 5 has to hold. So this side to this side must be the same thing as this side to this side. Do you see how I don't give a shit about that side? It didn't ask me or give me anything about that side. I don't need it. So how do you solve this? You can do what we just talked about. Cross multiply so you get right. And of course, can you see 3 times what is 12? 4. And 5 times 4 is 20, right? So this was just a multiple of 4. I just took that triangle and made it 4 times bigger. So they're not going to give you numbers that are always nice, of course, but this is the way these similar triangles work. They don't even have to be right triangles. What about this one? What do you got, Jeff? I don't know, man. All right. Oh, green. Not having a good day. Let's say oh, that didn't look right. Let's say 4, 5. I like it. Yeah, dude, I like it. You would, Jeff. So you do the same thing. I have to give you a little bit of reference. I don't know how they do this in the book. Just so you know, things I'm going to turn around. So what's one ratio you can set up? Okay, you could do, yeah. So this side to that side. This side to that side equals this side to that side. So that's a ratio you can set up. Now real quick, on the side I want to show you, you could also set up small triangle side to big triangle side equals small to big. Some of you guys might realize, once I cross multiply, don't I get 5 times x? So you see how that still makes sense? So there are kind of multiple ratios you can set up, but they have to be, the definition of the top and the bottom has to stay the same. So if it's small side to big side, then this one has got to be small side to big side. If it's this side to that side, then this one better be this side to that side. As long as they're defined the same way, that ratio equality has to hold. So what do you get when you do this? Good. 4x plus 12. Got to distribute. Equals 5x. Subtract 4x. You get x is 12, but you're not done. 15. I like it. So the idea of similar triangles is really nice. It sets itself up to cross multiplication immediately with the ratios you can make. That is certainly a lot easier than the full-out word problems you were doing a minute ago. Okay, so that's 7, 7. 7, 7 is this and the word problems. Yep. I'm not telling you. It goes up through 7, 4. A little preview of chapter 8. Let me do one thing that's related to something in chapter 8. And let me say it like this. I will do one thing related to chapter 8. I'll need you later. Just remember what absolute value is. It's going to come back in 2 sections in chapter 8. So for example, what's the absolute value of -7? 7. What's the absolute value of 5? 5. What's the absolute value do to something? It makes it come out positive. Or 0. Because what's the absolute value of 0? 0. With me? So it's the most single-minded function there is. It just makes it positive. So if it's already positive, what does it actually do? Nothing. If it's not positive yet, what does it do? And how do you do that mathematically? What would you do to -7 to make it become 7? What would you do to it? Yes. So see, I hesitate to say this because students don't quite hear me correctly. I wish they had never made this symbol up. Now, at this level, you go up a little bit in math and the symbol means something bigger and then it becomes important. Because what this does, you ready? Here's what I want to talk about. What the shit is that? The answer cannot be x. Because what cannot come out of an absolute value? What can the absolute value not end up being? Negative. What could x be? Anything. So it could be negative, right? So I can't say the absolute value of x equals x. What if x is -7? The answer is not -7, it's 7. Oh, shit. So here's the reason why I don't like this symbol to be shown so early in mathematics. But it still has a purpose, don't get me wrong. So people here, they're like, oh, I didn't like it, let's just not worry about it. No, shit, we got to do it. And now when I start making equations with this in it, then I definitely need it. So there is a purpose. But here's the fundamental problem. That one symbol does 2 things, 2 different things. If x is greater than or equal to 0, if x is positive, what does it do to what's inside? Nothing. If x is negative, what does it do to what's inside? Yes. Students see this and they say, no, I thought the absolute value can't be negative. But what does it say? Negative times negative. Isn't x negative in this row? What's negative times negative? Positive. But this is why this symbol is kind of evil, because it hides the fact that it does 2 different things. So this is going to become huge. When we have an equation with an absolute value in it, there are going to be 2 situations we have to look at. 2 possible answers we're going to get. Okay, I think it's enough.
Will we ever get a single variable like that?
Yeah, sure. Yeah. You know, for example, if I said this, what's the answers? And 4. You get 2 answers. Now, then they get more complicated, but it's still built off the idea of 2 cases, because they don't know what the hell this thing is inside. 2 cases, yeah. Ooh. Not quite, but yeah. It's not quite quantum mechanics or anything.